Welcome back, everybody. We'll start what I think it's almost the last lecture, because next one is going to be seminar, and then we'll have some sort of lecture seminar. So today we'll be talking about planning under uncertainty. This is based on most of the things we discussed before. So I mean, on last lecture we start introducing nature, randomness, and these effects. On lecture 5 we talk about dynamic programming. So on today's lecture we kind of bring together the two topics. Well, let's say that the summary is as follows. We have uncertainty in state propagation. We have the Markov property that we want to discuss. We'll see that this is very important. Otherwise, well, all these approaches do not work well. We also have this concept of reward and return. We will discuss Markov decision processes, right? So this is the main topic from today. What is an stochastic policy, Bellman equation, and then a little more advanced topics that are related to partially observable MDPs and some belief state space planning. Okay, give me a second. Okay, so let's discuss a little bit more about uncertainty, right? This is one of the most limiting factors that we see when we deploy any real system in reality. Our simulations, our TOW environments work very well, but let's say that reality has always some limitations. We start discussing about this last time. So this was like this mysterious and unpredictable other agent. This is a way of naming it, if you want. But in general, this is also referred as noise, right? So we have here this real system, and either because you think about it as nature actuating on your system, or because it's simply imperfections on your modeling, there's going to be a little mismatch between what you are planning to do, what you think you want to do, and what actually really happened, right? So we see examples of this. Maybe you close your eyes, you touch something, and maybe your hand is not exactly where you thought it should be, right? So, well, you can do the experiment later. That's why we have like continuous feedback from your eyes, and then you adjust things a little bit. But the same happens for other systems, right? Like for instance, here, well, we shared this example with you in the Telegram chat. This was the old problem set 4. Here what we have is the evader that needs to get to the goal. And here what we have is a pursuer. It's just trying to catch the evader. And the problem was, okay, so I don't know what the pursuer is going to be doing. I have some ideas, but I don't know what it's going to be doing. And we were modeling this on different ways, right? So on the task, well, inside this is just a simple policy, but still is an stochastic policy. We don't know for sure, and there was some randomness, and the evader had to escape. Another example is this. So maybe you plan to just go ahead, and there's some little imperfections on the terrain, and as a result, the trajectory that this robot followed was not exactly like this, but it was slightly off. Okay, even a little bit, right? So maybe it's not like too much, depends on the level of the noise, but the truth is that there's a mismatch, right? We should always account for this. The world, anything that is running there, we might not be modeling it, all its elements, right? So this little mismatch, most of the times, is just considered as random variables and a probabilistic process going under the hood. Okay, so now we can discuss a little bit about transition between states. This is, I think, the third time that we talk a little bit about transitions, but not really going into much details. If you remember, on lecture 2, we were discussing transition of just moving from one position on the grid to the other, right? So that was just applying an action. This transition was kind of easy. Then on lecture 6, we also discussed about the transition equation. So this is from lecture 2, from lecture 6, if I remember correctly. This is the transition equation, right? From this, we were, we were suggesting, we didn't show this, but if you integrate this over some period, what you get is a transition function. And the transition function looks like this, okay? You just have the next state, and you have a function. And here, what I want to start talking about is the uncertainty. How can we model this uncertainty? So maybe some of you that already did this course on perception in robotics, this sounds familiar to you, right? There are several ways of taking this into account. The first one is this uncertainty is directly in the action space. Okay, so what it means is that you have an action and you are adding the noise to the action. Say that maybe the action is not just going right and left, but maybe you put a velocity, right? So the noise is going to be there. On this velocity, say you want to go at 1 meter per second, but it turns out to be 1.1. This is what you executed, or a little bit less. Well, this affects a little bit differently the transition function. And the same happens if you consider this uncertainty to be directly in the state space. So what is this? You have your state, you have your action. By the way, little note here, we are updating or kind of changing the nomenclature now. Before we were using states as X and actions as U. For this lecture, I'm changing a little bit because we are also following Sutton's and Bartu book on MDPs. But here you just need to do this little map. Every state is S, before it was X, and every action before it was U, and now we have actions A. Okay? Yes, so what is an example of this uncertainty in the state space? Let's say that on the previous problem, you propagate whatever action it is you have here, and then to this you are adding this random variable to the propagated state, right? You don't care about actions, you don't care about how you're propagating things. You kind of take it away, right? So this is what we are saying. You have a transition, and then you add a little bit noise. It has consequences, but I think for now we don't care too much. Maybe if you have to implement things for your final project, maybe you need to consider this a little bit. But let's say that they are just different ways of considering uncertainty. Okay. Yes, since we have now a random variable involved, what we can do is build this transition probability from any state and an action to a new state, right? So what it means is this. We have this probability. Remember that we are going to be discussing today about tabular methods. That means that we have a finite set of states. We don't have infinite numbers like continuous spaces as we were discussing. We have some of them, and then what we have is a clear way, for instance, positions in the maze, or things that can be discretized, and we have a discrete set of elements, and then we also have a discrete set of actions. Okay? So if we have these conditions, we can formulate it this way, right? We have this transition probability, and then it only depends on these two things. Depends on the previous state, depends on the action, and then there's going to be a distribution, or if you want, different values assigned to these new states that, well, we have available. We know about them, right? This is the other strong requirement. We know about this transition probability. Okay, but have in mind that I'm not talking here about continuous distributions. They are discrete. So we have a discrete set of elements. Otherwise, well, MDPs will be a little, well, we'll need to redefine them a little bit. Okay, so this topic was already discussed on the last lecture when we were talking about one path, one length game. And then we start saying, okay, and now what happens if you play continuously, right? So basically what we have are sequences of states. So the same happens here. A plan is executed, right? We follow this sequence of actions, remember, or we were following a sequence of states, depends on what is the solution that we have calculated. But then what we do is propagate them over time, okay? So for the deterministic case, this was a simple example. You know for sure what's going to happen. You just have your sequence of actions, let's say. You execute one after the other, and you know for sure that you are going to achieve your goal, or whatever point you have calculated, right? Now, what we have is that it's not exactly true, right? Because every time that we propagate this state, there's going to be a little bit perturbation. There's going to be a little uncertainty on what's going to be the new state, either because it's defined in the action space or in the state space, but it's not going to be exactly what we think it's going to be, right? So that means that we need to determine all these random variables affecting the propagation. And now things start being complicated, right? Because here, if we have time from 1 to final capital T, right? Whole sequence, the whole trajectory, if you want, of the plan. Now what we have is that we need to unroll all this propagation, all this sequence of propagations, and for each of them, there's going to be a random variable, right? So you see that this thing starts becoming a little tedious to write. So here we have a lot of functions of functions of functions, but the thing is that for each of them there was a random variable. So we cannot really now know for sure that this is going to have just a single output. It's going to be a distribution, right? So if we write this in recursive form, what we can see is that at the end, what we see is this final state is going to depend on this long sequence of actions and states, right? So this is basically the trajectory. So this is a little inconvenient, right? I think I'm just motivating the example, don't worry. We'll find a solution in the next slides. But the moment that we start talking about distributions, you see how things get more complicated. We need to take into account literally almost every outcome, because now there's randomness here involved, right? So we see that if we consider a sequence, this is complicated things significantly. Okay, so that's the motivation to present the Markov property. It's not for convenience, right? There's other reasons, there's other motivations, but I just wanted to show that actually if we consider the proper case of no assumption, all random variables are here considered, what we have is a high dimensional probability, transition probability, right? This is high dimensional because we need to take into account everything. Everything counts. Whatever you did in the morning counts until you get here, kind of, right? The Markov property on the other side, what it's doing is simplifying this real assumption, but it's simplifying it a little bit, okay? Maybe some of you heard about Markov property, right? Yes, you did. You did, yes. Okay, so what is it? It's kind of saying, and I'm just writing here things a little bit informally, that the future only depends on the present, right? So it only matters your current state now. It doesn't matter how you get here, right? So it doesn't matter what you did in the morning once you are sitting here in class. This is the Markov assumption, okay? Maybe it matters. But for this property, it only matters that you are here, you are with this current state, sitting here, and maybe if you do any other action, you move, you do whatever, from here, it doesn't matter where you were in the morning, right? For instance, if you get out of the door, it's only going to depend where you are now. Nothing else matters, right? You just get up and follow the door. Or, well, other things. I hope everyone stays sit, by the way. Okay, so this has also this side part that I was not. So you discard the past, right? So this is a strong assumption that we are doing. For some processes, okay, it matters, right? So it matters what you did 1 year ago. It matters for yourself and for other things. But maybe if we are just considering more simple tasks, like we need to move this chair from this door, from this room to the other, maybe it doesn't matter, it's full past, right? So this is a little bit the motivation of why using the Markov property makes sense, and why we'll see that this actually simplifies a lot this high-dimensional probability transition. Right? More formally, what it means is this. We have here the full trajectory. Here, if you want, you can also add actions, right? Well, I think for this example, I was not including actions. But you basically have a full trajectory. This is all previous states, and all of them got discarded. It doesn't matter. The only state that matters for this probability transition is the current state. So this is what it's saying now. The chair is here. You're going to move this to the next room. It only matters where it is now, not where it came from. Okay, we see now that we have less requirements, so the dimensionality of this is less, right? We don't need to consider full history, full trajectory, so this is great. Just to summarize, this at time t, we are capturing all relevant information, right? If that's not true, then maybe we need to consider the past history as well. Maybe not to the infinite origin of time, of course, that's going to be, but maybe there should be some origin where things start affecting, or basically they condition your transition, yes, the transition probability here. Another advantage is that there's no need to store past states. Right, so this is also very helpful. If you don't need to store them, that means that there are less requirements for us to work. Right, so we know that keeping things in memory is sometimes important. Remember, for instance, graph search. It needed to go over all elements. Value iteration. You need to keep in memory all elements. Even though that the local operator is easy to solve, you still need to go over all elements. Who has done problem set 3 or is close to it? Okay, awesome. Very good, almost. Okay. Yes. So, well, with this, you will see that this lecture actually is very related to value iteration. Very. Okay, so as I was saying, this same idea of the Markov property could be applied to probability transitions. Okay, if you want, yes, I'm just writing things again for actions, but it's kind of the same idea. You have your previous state, you have your action, the previous action you are executing, and then the new state is just going to depend on this, not on the full history. Okay. This is one of the main principles of today's class. Everything is built around the Markov assumption. It's an assumption, again. It doesn't mean it always holds. But without this, the computational requirements are going to be higher. Okay, good. So everyone agrees, then let's see a little bit example of this, right? So this, well, let's call now them Markov process, right? let's say that the most straightforward for us to show an example of the Markov property is via a Markov process or a Markov chain. Okay? So what we can do here is just write the probability transition. Here what we have is S new. Just going to show some examples, not all of them. And here what we have is pairs of actions and states. Okay? So if you have this this Markov chain with the states, nodes in the graph, and its transitions, then we can just create this probability, this transition probability, right? Why not? This is just a graphical model, but we could be getting this from here. So let's start with this, right? So we are in state 1. And let's say that we have 2 actions in state 1. Okay? We have action 1 and we have action 2. Just by looking at the graph, do you see any other action? I'm looking for arrows that just get out from this node, right? So we have other arrows that are getting into the node, so that's actions for other states. But in this case, well, I just see like these 2 actions, right? So in this case, we'll have this. So action 1, state 1, right? The resulting new state is S4, and this probability is 0.1. Okay, so the only thing I'm doing is just taking whatever we have on the graph and doing this. And the same could be done for the other action that is here, right? So if you execute action 2, what we will get is that we get to the new state is going to be state 2, and this probability is 0.9. Okay, you could be doing this as much as you want. There are some properties, of course, that need to hold. And basically, well, you see that the sum of this is equal to 1. So if you are in one state and you apply all actions, you should have full certainty, right? There's no other thing. So if you apply all available actions, if this thing was not sum 1, that means that there's some other action that we are not considering or some other state that is not there, right? Let's say that this, right? Maybe you state in the same state. But this we know because the values on the other, that this has to be impossible, not happening, according to this transition equation, okay? Transition probability, sorry. Okay, you keep doing this. You need to make sure that sum is 1. And, well, this is just a way for you to have, like, all these transitions into one table. Okay, well, this is just an example. Now, the new component that we can discuss, so we have talked about transitions, all agree that with Markov property we have a great, we have reduced significantly the variables, but now we have an extra component, right? So let's say that at each time step, it's not just the transitions that we are looking for, but there's also a reward. There's some value that is taking into account how positive, how rewarding, or if you want the opposite, how punishing is to do some action or just to do some, to be in some state. For instance, if you are like hitting to a wall, maybe that's a not very good reward. While maybe if you are like already in the goal, this goal that you want to achieve for planning, this is a very positive and high value reward. Okay? So the example is a little bit this. At each time step, so this is a little bit the difference that we are defining now. It's just a number. Let's put it like this. So then the agent's goal is to maximize the total amount of reward it receives, right? So as you are executing your plan, you want to maximize this reward. We already talked about this when we were presenting Dijkstra E star, right? So there was like some cost associated to traversing. We wanted to minimize this. Now, instead of cost, we are shifting a little bit, and instead of, because cost penalizes, right? But rewards. Okay, so it's just different name for the same thing. One thing, cost is usually minimized, so you want to minimize the cost. Rewards is usually maximized. You want to find out what is the maximum. But it's kind of the same thing. All of them would yield the same solution. Okay, so what we do is we accumulate this over time, and then what is this reward hypothesis, right? All of what we mean by goals and purposes can be thought as a maximization of this expected value of the cumulative sum of a reward signal and this received signal, and this is what we call reward. Okay, so as we go, because remember, here now we are in this, we have not a deterministic system. When we propagate things, we have discussed that there's going to be transition probabilities, and it's going to be stochastic, right? There's going to be some randomness here. But anyway, the hypothesis is that we want to maximize on average or on expectation this reward. Okay, so examples of this would be if you achieve your goal, you get +1. If you get a collision, you get -1. Okay, so this is a clear example of positive, achieving your goal, and negative, doing something else that is not really so, well, it doesn't help anyone, I guess. Yes, the students get their grades after submitting problem sets, so this is the same. You do some planning problem, and then you get a reward. You want to maximize this reward, right? Yes. Okay, yeah, very simple examples. I'm sure that all of you have maybe 10 more better examples than this one, but think about it. Okay, what about return? So return, I already introduced this, but return is this cumulative reward. So what it means is that, where am I? Here. Return means that you are just accumulating the reward over all time steps. Easy. Sum of all of them. Okay? This presents a problem for continuous tasks, right? Because they never end. Imagine, sometimes you don't know when things are going to end. We talk about observing states, right? So how can you formalize this in a nice way that you are going to have a return that is bounded, right? It's not considering all possible states for the infinite, time. So usually a very common approach when we have like this continuous task or infinite time plans, or, well, different names, but it's the same idea. What we can define is a discount rate. So this is just a number, and the idea is that as we go farther in time, we are just penalizing more and more the reward that we are getting. What is the motivation of this? Because things that are happening now are more certain, let's say. Things that happen in a very long future might not be affecting you so much. Still, you want to maximize for infinite times. But we know that this series converges into bounded value, right? You can do the summation of infinite numbers of this geometric norm plus some real value that is also bounded, right? I mean, I didn't discuss properties of reward, but it's not an infinite number. It's a bounded number. And well, with this, we'll see that still you can plan. Sorry, you have a question? No, it doesn't converge to a particular number. But what I mean is that this is not unbounded. This doesn't converge to infinite. If Exactly. If you didn't have this discount rate, you were just doing like this for t going to infinity, you might have an infinity number. Because you have infinite number of elements, you are just summing. But because you have this geometric power here of this discount value, then this converges to a finite value. So this is also very important. This is the only reason why discount rate allows you to have infinite horizon problems. Okay, so the thing is, we could unite both returns. It means return without discount rate and this one with discount rate, if we consider a terminal action. So if we consider this terminal action, then maybe the reward is going to be 0 at some point, right? And then you are going to add zeros. And then this is not true anymore. I mean, maybe it doesn't converge. But it's kind of a little more artificial, I would say. But still, you don't need then to apply the discount rate. But if you don't want to go into this, you don't want to take care of these absorbing states, the discount rate is very popular and I would say very common approach of solving things. Okay, good. So now let's discuss a little bit about Markov decision processes. We have the final elements. We always do the same. Before kind of getting into definition of a planning problem, we want to define all their elements, right? We have already defined many times what states are and what actions are. Now we have rewards and returns. But let's say that we have now these new elements on the Markov decision processes that we definitely needed to talk about. Basically, you can consider an MDP as an environment with the following components, okay? We have an agent. This is our old robot, old agent that we have been discussing on the previous lecture. Whoever wants to solve some plan, some task, okay? Now, because of the randomness of the world, executing actions, all this uncertainty that happens because there's this gap between what we want to execute and what actually we execute, what is the return, we need to model this as an environment, let's say nature or other parts that are simply affecting a little bit how these transitions are going to look like, okay? So you just execute an action, you have your current state, but then it's not deterministic what is going to be the output state, right? So we know that, for instance, we have now a table just with all probabilities of going from one state to the other. Not all of them are possible, but definitely it's going to be common to have several states with some little probabilities, some probabilities. We also have a reward, okay? So what is this? This is measuring like how well we are doing. Let's say that, yes, maybe this is not the result of the environment. Once you have the state, you can calculate it. And once you have this, you basically iterate over and over again, right? So this is the transition function that we were talking about, but now differentiating a little bit, right? So before it was just talking about a random variable and then you execute things. But now we are adding all elements into this nice diagram, right, where we are separating what the agent is doing and what the environment is doing. Okay, yes, this is a very valid or very general scheme, right? So you will find this in other problems. Yes, mostly when, let's say, we execute things in the world. We could be adding more layers of complexity. We'll talk about this when we get to the end of the class. Okay, so a little more formally, let's define all these elements. All of them are familiar to you already. The only thing that is kind of new is this environment, but I think it's well understood after we discussed about nature and games in the previous lecture. Formally, an MDP is this tuple that contains all these components, and I'm just describing them here. Finite set of states. Check. We know about this, we know why. So if we have infinite or continuous, then we know that there's going to be a little bit issues, right? So this was lecture 5. We have a finite set of actions. This is also known, right? So when we were discussing about value iteration, we already discussed about finite number of actions. This is the new thing. This is how we are kind of defining the environment. This transition probability. We know that we can just write this as a matrix, right? We have some dependencies, and then what we have is what is the output, what is the probability associated, and what is the new state. And then this new thing that we were discussing is the reward function, right? Because we have this probabilistic nature, we cannot just calculate the reward for a particular action and for a particular state, but we need to average them. And for this, what we have is the expectation operator. Yes, tell me. Okay. Think about this as the reward that we have discussed before, but now average over all possible outcomes. Okay? So the motivation of doing the averaging is because when you execute an action, you don't have any guarantee that the new state is going to be unique. It could be like you go a little to the left, you go a little to the right. Both options are correct from the transition point of view because we have an environment that is uncertain. You don't know what's going to happen. So that means that you need to consider all possible outcomes. Okay? So the moment that you have all possible outcomes, you cannot just take a single number. You need to average all of them. And this average is weighted by its probability, right? So this is what the expectation is doing. It's just kind of telling you, okay, you execute this action. Let me give you an example. There's a high chance of, if you want to, stand up, there's a high chance that, yes, you will move and you will get. But there's a very small chance that maybe you fall. Okay? Still, is this likely? Probably it's not very likely. But when you want to calculate what is the average result, you want to calculate both. Right? So imagine, when you go on these stairs, you might fall. So this is capturing this kind of event. It's very unlikely. Maybe this transition is very, very small, very unlikely that you end up on the floor. But still, for considering all possible outcomes, you need to take this into account. Okay, maybe more uncertain things are not you walking on the stairs, but let's say me flipping the pen. I might take it, or it might go to the floor, right? So. Mm-hmm. Okay, yes. So let me elaborate a little bit on the example that you were asking. Let's say that you add 10 if you stand up. So the question is, okay, how can we, and I'm just giving numbers, it could be anything. And really falling down, it's going to be very penalizing, right? Because this is very hurtful. So this is falling, and this is standing. But now, let's say that your probability transition looks like this. So okay, I think you only have one state. Yes, you only have one. Okay, let's say that, yes, you have previous state, you have the action that you are doing. Let's say that you only have one. And then you have two possible new states, right? One is standing, and the other is falling. These probabilities might be like very big, and this one might be very small. Okay, let's put it like this. Okay, so when you calculate the reward, the average reward might be very close to 10. right? Well, okay. Let me add this, 9. More numbers. How many times can you stand up and sit in your life? Like a lot of them. Okay, I'm not sure about the number. But what I want to say is that when you do the average of this reward, maybe what you get is something like this. The probability of standing multiplied by its value, plus the probability of falling multiplied by its value. So what we have here is 10 to the 9 multiplied by 1,000, so we still have here 10 to the minus 6, and here what we have is almost 1 multiplied by 10. So you see that this result is almost 10. It's almost going to be guaranteed that yes, you are going to stand. But depending on the probabilities, this could be more critical, okay? So it's clear what to do here. If you want to stand, you stand. There's no risk of, well, falling. It could happen, right? But if you do the average, this is, if you have these transition probabilities, this is what it's going to be telling you. So you should not be thinking, oh, should I be standing up now or maybe not? So usually there's like no decision to be done here. But if it's more complicated thing, imagine you want to stand up with one hand, or more complicated things, maybe the distributions change, and then your probability of falling is higher. At the end, what you want to do is maximize your reward. So this is the kind of idea. Okay. Well, just another example. And we have the final element, that is this discount factor, so any number. We have all these elements, and we have an MDP. We have a Markov decision process. Okay, very good. So after defining these components, we can also do a simplification in notation, right? Because what we have here is, first of all, the probability transition, and now what we have is this joint probability. This is following Sutton and Bartos' book. What they have defined, just to simplify things a lot, because if not, you have a lot of elements here and there, and a lot of other stuff. They have defined a single unique joint probability considering the next state and the reward. So imagine in your table what you have now is not just the next state, but also this transition is giving you what is the reward. Okay, so if you want, you can add a second element to the output. Not really a big deal. It's conditioned by the previous state and the action, and the output is next reward and next state. Okay, so how is this then used? We can express all required elements in the MDP in terms of this joint probability calculated here, right? So for instance, what is the definition of the expected reward? Okay, so we write it like this. We know that the expected reward is, well, written like this, but if you want to look in more detail about the numbers, what you do is this, okay? So for each value that you are considering in the reward, what you are calculating is all possible outcomes. All possible outcomes, what it means is all possible states. So, here, have you heard about total probability law? So we are just marginalizing this variable just by considering all its terms. Okay, don't worry. These are standard things from expectation on discrete sets of elements. Take a look at this. I recommend you to take a look at the book also if you want to read a little bit more about it. But yes, the idea is that the variable that we are calculating this expectation, so the distribution that this expectation is calculated on is the next state. You have a different distribution of these next states, okay? And then you want to calculate, so these are the ST plus 1. You want to calculate what is this average reward that you should be expecting from them. So this is the only thing we are saying here. Okay, state transition probabilities. So the same thing. This was the table that we were using before, And what we are saying now is that, okay, now what we want to do is marginalize our reward. So all these probabilities that depend on R, we just do summation to average with respect to them, right? So they simply, well, disappear, if you want to think about it, or they get marginalized. And then, yes, we have the previous transition probability. The same for the expected reward, right? So it's compact way just from this single probability to define all the components that we need. Okay, I'm going to let you maybe give a look on this. And after the break, we'll do an example, just showing all these things, okay? So you will see a little more clear what we mean by this. So if you're not familiar with this derivation, this is just standard things from expectation, but I think you just read it, you see, and then on the paper, and then you will see this a little bit more clear. Okay? After the break, we'll do another example showing an MDP in action. Let's get back to this example, right? I was defining all these terms. All of them are necessary. I'm just going to put, again, with some table, what is happening here. Let's consider this. We have the following problem. This is also, by the way, a transition graph. It's maybe a little more compact way of expressing all these kind of problems, because now we have a lot of different elements, right? We have actions, we have states. So this is a way to put them together in more understandable way. So what we have is states with these circular nodes. Actions are, if you want, small dots. So for every state, there's a set of actions that get out. And from these actions, what we see is what is the new state. Okay, so in this case, this state didn't change, applying this action. But what we see for this other state is that there were two possible outcomes. Okay? One is changing to a new state, and the other is just maintaining the same state. So let's explain a little bit, because you will see this more clear. Let's say that we are in a car. The only action you need to do is press gas, right? So if you want to move, you need to press gas. I'm simplifying a lot what driving a car is, right? But we have this initial state, that is, we are stopped. Okay. We are stopped, okay? And our action is, so we are here. Our action is do nothing. Okay? We are sitting in the car, we have a gas pedal, but our action that we are doing now is do nothing. So, what is the most likely thing that is going to happen? That the car stays the same, stays stopped. Okay? So this is what I'm writing here with numbers. The probability transition, if you are stopped, you do nothing, is going to be 1 according to this transition graph, by the way. Maybe you have other problem that is not exactly 0. And let's say that we are assigning a reward that is just 0, right? So you didn't do very well. Okay, this is exemplified here. You have one action, and there's only one outcome from this transition. So if you want to think about it, this is a deterministic case. We're still encoding this with the transition matrix, but still, this is more a probabilistic case. You do nothing here, we are sure that nothing is going to happen. Okay, let's move on now to maybe more probabilistic case, and it starts the same. It starts with you stop, you apply some gas, you want to move, do something, and then the result, unluckily, is you stay stopped. Maybe you have a very old car, or there's something broken, we don't know, right? But let's say that this is already a probabilistic process going on. The environment is affecting you. You want to run things, but the environment is not allowing this. So here, I'm just going to give like, let's say, small probability of this happening, just making up this example. Okay? And let's say that you don't have a nice reward. You have a -1, whatever. Okay. The other example is we start to stop. We move. So the car starts moving. And the action was we didn't do anything. Okay? Can anyone tell me what's going to be the probability here? 0. Yes, correct. Exactly. Because if you consider the full joint probability of all events, the summation of this could not be more than 1, right? So we know that all possible events are, well, it's probability 1 that any of the possible events are going to happen, right? And in this case, this event of your stop, you do this action, has already probability 1. So if you sum these two things, it should be 1. It cannot be bigger than 1, right? So this is not possible. Not because the car does not want to move magically, but because we already defined what happens when you do nothing, right? So if this has probability 1, this must have probability 0. So, okay, let's see the other example. We are stop, and then the next state is we move, and we have applied some gas. So this is the usual case. In this case, it's going to be this, okay? So you see that now we have a lot of arrows. That's why the transition graphs helps sometimes if you need to sketch the problem. And this for the same rule, right? So the summation of all probabilities of the next state should be equal to 1. So we already have these two, I mean, I'm going to put it in this color. These two things here are the same. No, sorry, this and this. We give gas, action, and previous state are the same. So that means that the summation of this should be equal to 1 as well, right? So that means that here we have this. And then, well, I guess this is, yes, plus 1. Okay, I'm just making up the example, but it's important to understand how these tables look like. At the end, they are just high-dimensional probability distributions with discrete states. So in this case, yes, what we have is just values of each of these probability transitions. But sometimes it's a little abstract. With this example, it might be a little more clear. Okay, now that we have, well, this example, we have put all, let me also talk about a new extra element that I didn't really discuss much. We have defined all elements, but now we want to find a solution. And I'm going to tell you that this is going to be more likely in form of a policy. But I want to discuss a new kind of policies that is the stochastic policy. Okay, so just to refresh the concept, what we studied previously as a policy was this deterministic policy. We have a state and its output an action. It could be the best one, it could be any other action. But what we had is just a function mapping states to actions. Okay, there was nothing going on, nothing strange. What we have now is a little bit different, right? We want to model this uncertainty. So this is also going to be something we can model here on the policies. So for this, we will define what is called an stochastic policy. What is this? This is a probability. Okay, so if before it was just kind of a function giving you an action, what we have now is a probability. For discrete spaces, right? For others, you will have a distribution. It's reflecting this randomness, right, by whatever the environment is doing. And we can think about it as something like this. Okay, we'll make use of the same nomenclature, so we will use pi forward policies, but now they are writing like this, conditioned by the previous state. And it's simply that. What is the action of this? What is the probability of this action happening given that we have the previous state? Okay? So before, what we were saying is, we just have the state, give me an action. This was your policy, right? It was like, no brain, you just give me, if you give me this state, I'm going to give you an action. Now, what you are having is discrete set of probabilities, right? You will see exactly what is this probability of actions depending on the previous state. So this gives a little bit of uncertainty. What's the action you are going to execute? Why don't you execute a single action? Maybe there's noise. Maybe you want to execute that, but so we'll see that stochastic policies actually make sense in this MDP formulation, but it's just adding a little bit more complexity into the problem. So as a result, we can have kind of the same problem as before. Actually, to calculate what is this distribution of actions, you need to calculate all previous states and all previous actions that you have taken. Now what we do is we apply the Markovian assumption. So we motivated this before, but I think at this point you are convinced that if you just give the current state, you have enough information to give you this distribution of actions. Okay. So this is it for stochastic policies, and now we get into the interesting stuff. Now we start discussing on how we can solve the problem. Right? So far I was just talking about elements. I was just introducing distributions, transitions, a stochastic policy now, all elements. By themselves they didn't mean anything. Okay? But now what we want is to solve the problem. We want to find the action to take. What is the plan? Right? This is what the course is about. What is the plan that we can calculate if we want, in this case, to maximize the reward? Okay? So let's discussing it. For this, I'm going to define, this should be familiar, the state value function. I'm grading a little bit differently, so it's not exactly as before, but what we are grading is the state value function for policy pi. Okay? Because of the randomness of the reward, we don't know what's the reward that is going to happen. We don't know the transition of the state. There's many unknowns. What we need to do is calculate the expectation of the return. Right? Remember that the return, in case of the infinite horizon problems, look like this. It's just a summation of all your rewards. And this is, well, what we are seeing here is that this is conditioned by the state S, right? So at the end, this is going to be just a function that you give the current state, okay? So think about it. B of pi of S, what it's doing is you have a state, okay? Forget about all things that are happening inside. We don't care too much. But this function, we know that it's going to give us a value, a real value, okay? This is familiar from lecture 5. Remember how we were obtaining the value iteration, right? At the beginning, we start with the same. You have the summation, but you know that there's going to be a way, actually, a recursive way for us to calculate what is this optimal value and what actions we can take from this. The new elements now is considering them in a probabilistic way. So we have expectations now. Here, note that this is with respect to the policy, some policy we are calculating, right? This policy, by the way, is of a stochastic nature. It's going to be not, I mean, given a state, you don't know what's going to be the output. It's going to be some different probabilities for some different actions. But it doesn't matter for this because we just average this, right? So this is how we work. In the long term, if you average all possible outcomes, you should get the expected value. Okay, so we can also define the same thing, but now for this pair of values action states, right? So this is the Q function. It's also used in many other places, right? For some things, it's going to be more convenient to work with Q functions. Just think about it as you have your previous value, and the only thing you are adding is an extra dimension to your table. So if before your value function, it was just mapping states to values, now what you have is pair of state and the action you would be executing. And this is going to give you just what is the expected value, or the cost to go value, if you want. Okay, if you remember, it was this one. Okay, so we have put summatory here. So far, we didn't say anything. We just said, look, okay, fine. If you execute this policy, you execute this policy on a sequence. This is the reward that you are going to have. You're going to have this value. I'm not saying it's good. I'm not saying it's bad. I'm just saying that if you execute this given policy, you are going to have a value that could be mapped like this, just with the current state and nothing else. So now comes again the Bellman equation, right? From this value state function that we have defined, we need to identify this recursive term. This is how we did this last time. If you remember, we started with the tail problem, right? So we were just taking the tail problem, and then we were every time adding a little bit more to the left, just because we were calculating the cost to go. We could be doing this from the beginning as well, right, in forward motion, but, well, things change a little bit. The thing is, we need to find a recursive form. So this is what we are going to be doing here. It's simply a little more clutter, because instead of having just rewards that we are summing, we have an expectation operator. But the expectation operator is a linear operator, allows us to do some manipulations, and we'll see that there's still a recursive form that appears. Okay? So this is the definition written in the previous slide. What I'm doing here is I'm just separating things. So I'm just taking all of them, all the tape problem, plus RT here, plus 1. Okay? And for this, we are expanding what this RT means. Right? So we need to take things out from the expectation. We need to manipulate a little bit. But at the end, what you see is that there's a recursive form that appears. Okay? So this is how we see the Bellman equation appearing. We do this manipulation. Now we have a lot of summations with respect of transitions and other things. This is necessary because we need to average things, right? So we need to take into account all possible outcomes and weight them by their probabilities. We need to take this stochastic or this probabilistic approach of considering all possible outcomes. It's not anymore deterministic. So if you do this operation, this manipulation, we'll see that at the end what we get is the same value state function that appears inside this recursive form. And this is very, very similar to what we got before, right? No? You don't agree? Okay, okay. It's for you later to check. You want to compare maybe lecture 5, dynamic programming solution that we get with this equation. You need to find, you need to identify what are the common parts. This thing, you can do the derivation. I'm just taking elements here. Nothing fancy. But if you put the two things together, you will see the similarities. And this is the most remarkable one, right? The moment that you see that value state appears again inside this function, this is great, because then we know that we can apply dynamic programming, right? I mean, we are deriving it. Remember that we discussed about dynamic programming more from optimality of paths, right? But you can also derive this mathematically. So at the end, if you see this recursive form, this is a way of dynamic programming. Okay, so another way is if you don't want to solve dynamic programming, you could be solving this equation directly if you want. You have a lot of elements in V, a lot of transitions here, so this is given. You have elements of B. You could be solving this equation directly. But I think dynamic programming is good, just to start understanding now the problem. Okay, so Now we see that after all these new elements that we have described, all these probabilities, randomness in the environment, we have obtained recursive form that allows us to use dynamic programming. So let's see how we can use this to obtain these optimal value functions. Okay? So the key thing is that this previous example, we were never questioning about the policy. The policy was always the same, right? So you have the policy here, you are not optimizing with respect to this. We are just saying, look, if you have this policy and you apply dynamic programming here, this is the cost to go function that you are going to have. So what we do is you execute things many times, you apply dynamic programming, and you get this known cost to go to the end of it. But it doesn't mean it's good. It doesn't mean it's optimal. It's just one policy. So now what we want to do is optimize this. Okay? From all rewards that we are getting, we want to optimize them. We want to maximize the reward. Right? Remember that now we are maximizing things. So for this, what we need to define is this optimal state value function. And the only difference is that here we are going to do a maximization with respect to all possible policies. Okay, and this might look a little troubling at the beginning. So can you optimize about policies? But let me just put it this way. Okay, so from all possible policies, imagine that, yes, we can list them. We are going to find this state value function that gives us the best solution ever. Best return, best reward, accumulated reward. This is what we want, right? So this is what optimal means. Best in the sense of maximum return. Okay, so far everybody agrees, right? I'm not saying exactly how these policies look like, but I'm just saying that if we could list them, we'll be looking for the policy that is giving us this best. And there's no other policy that is giving anything better. Okay? This is tricky, but it's the key of this derivation. Yes, so we compare all possible policies. The same could be done for action value functions, right? It's just doing the same. Here we are just looking for best Q function possible, right? Okay, well, yes, we can also write it this way. Okay, so now that you are convinced that we need to find this best policy ever, let's rewrite things a little bit. It's the same derivation as I did before, but the only thing I'm doing now is considering maximization, right? So this is where we are considering the optimization part. Here, the thing we are maximizing is just the action, the next action, right? Okay, so you can do the derivation. Here I'm just rewriting things. So this is the definition, this is the definition. Here it's the same thing. We separate tail from the current problem, and then we write this in recursive form. Okay, so here we got Bellman equation again. And then what we get is this very interesting result. Here I'm just writing the expectation, right? So the expectation with respect to these pairs of next state and reward. This is what variables that the expectation is calculated on. We weight all these reward functions, and then what we do is from all these functions, what we want to find is what is the best action that we can take. Okay? So if we do it this way, then we have a way to calculate what is the best action. Okay? So, well, let's dig a little bit more into this. This Bellman optimality equation expresses the fact that this value of the state under the optimal policy must be equal to the expected return for the best action from the state. Okay, so there shouldn't be any other better value that we can get, right, if this is actually optimal. So there should not be any better optimal value here. This is a little bit the idea. There's nothing we can do that is going to give us any, a value that is better than this in terms of reward. So once the optimal Bellman equation has been solved, there is a simple way to calculate the policy. For instance, you could be saying that here what we are doing is a greedy policy. Okay, you calculate this. You have converged into a solution, right? You have converged into the optimal value state function. You have this. We've seen that actually, yes, you can do it this way. And then how can you calculate an action? Okay, so a way of doing this is not a deterministic, this is a deterministic policy. You just calculate what is the best action you can take. And again, this is going to be on expectation, right? But this is a way for you to give you the action to execute. Okay, so you need to ensure that this transition is not zero, but other than that, yes, this should give you the optimal, long-term optimal path. Okay, some examples of this. How is this used in practice? So remember, after we have converged, adding the maximization, after we have added all these transitions, there's going to be changes in the results you get from value iteration and changes you get from MDP. So this is an example of this. Here you have a goal, you have the initial state of the robot, and if we were calculating this on standard value iteration or any other planning algorithm, it doesn't take into account transition. Maybe it doesn't take into account collisions because everything is deterministic. And then the best thing you can do is just traverse the narrow passage. Maybe this is risky, and that's why this other algorithm that is calculated here, it's deciding, look, no. If you follow this kind of greedy policy, after calculating the optimal value state function, the best thing you can do is not get through the passage because it's going to be uncertain. There's going to be things that are going to affect your robot. Maybe, I don't know, you cannot control it well or whatever. So what the algorithm is telling you is, look, just take this not shortest path, but in average, if you do many times this thing, what you will be getting best results is if you follow this a little longer path. But overall, on expectation, you should get better reward. Okay? Okay, this intuition is clear. Somehow what is included here is this notion of risk. It's very funny. If you remember from problem set 1, that we have all these things getting always in touch with, when you were moving the rod on problem set 1, it was sometimes touching the wall. It was getting very close. And you might be thinking, if I was doing this myself, probably I would not be so close to walls, right? Especially if you start rotating things. Okay, maybe I thought about it. And the reason is, it doesn't matter. There's no way for capturing this. Where is this problem in your cost function? You either have a collision or you don't have a collision. So this was a very strict definition of the problem, right? So you either have a collision or you don't. You have a deterministic state, you know everything. But when you add uncertainty, then this thing is not so clear, right? So getting close to objects could be dangerous, right? Because you don't measure well depth, or because, well, again, the environment is uncertain. So this is the motivation for this. If you do it this way, of course you need transitions, then you will see that sometimes the shortest path is not the best one for overall reward, right? And this is just an example of this. Of course, there might be a lot of examples where the shortest path is also on average the best reward or the most rewarding one, right? So maybe this is a little bit extreme example with a very noisy robot, but to get the point, I think it's a good example. Okay, good. So on equations, I didn't develop them. You can do this later if you want. But the motivation is, once we have randomness, once we have uncertainty, things change a little bit. Maybe are less logical, but, well, we are just considering all possible outcomes, right? So this is what matters. Okay, some remarks. We need to know the dynamics of the environment. So this is really a limitation. Dynamics of the environment means the transition function. Well, transition function. Now we know that we have this in a transition transition probability, right? So we have a table with probabilities, but you need to know them well. If you don't know how your system is going to transition, if you apply an action, then you have more unknowns in your problem, and you definitely cannot use MDPs this way. Learning model-based approaches are based on this. So what you learn is dynamics, and then you apply other methods, MDP, for instance, or others. We have enough computational resources to complete the solution, right? So that's okay for tabular cases. Okay, relatively okay. If you have infinite number of elements, you know that solving dynamic programming is going to take a lot, because every iteration needs to take into account all the states. You need to do many iterations until convergence. Sometimes there's a little region that has not converged, but you still need to run things over and over again. And the other property is that the Markov property. Without the Markov property, this doesn't work. So without the Markov property, you need to do kind of rollouts of your trajectories all the time. You need to start from a point, you need to just develop things and see how they work. With the Markov property, we can apply dynamic programming. If not, we'll have other dependencies. So this is a little bit the hidden detail, right? In practice, direct MDP or other discretization is not easy to implement. And we will approximate solutions to MDP, right? So that means that taking some approximations or, well. And interestingly, there's even more complicated problems that what they try to do is approximate them to MDPs, because MDPs are still reasonable to solve, right? But now I'm going to give you an example of things that get a little bit more complicated, and, well, sometimes it's not possible to solve them. Okay, this is it, partially observable MDPs or PMDPs. This is just a very brief introduction. With what I have described with MDPs, you should grasp the idea, but the derivation gets a little bit more complicated. What we are saying here is that we have an extra layer of complexity, and it's the following. You never know for sure what is your state. You need to estimate this state, and you have some observations that is giving you this. Okay? So if you don't know directly your state, if you observe it, that means that you are going to have a distribution as well. So you need to estimate this, and on top of this, you need to do transitions, calculate rewards, do this with get until you get convergence. So it's much more complex. And remember that usually this has problems with dimensionality. So here we are adding more dimensionality to the problem. We have this new extra kind of dimension, if you want, relating all possible states with the observation you are getting. Okay, so basically, it's kind of solving a lot of things, but I would say that most of these approaches somehow need to relax the problem a little bit, solving PMDPs. So you either have a very small state space, or you take some considerations, maybe you use sampling. There's many techniques, but usually this is not feasible to do for larger spaces. And larger, maybe I mean 10 by 10 mazes, right? So it's kind of small. Just do the numbers. Tabular table is just going to explode, right? If you start adding observations, states, actions, a lot. Okay, this was more informal presentation of PMDPs. Maybe some of you are working with this, but for this we need another lecture just explaining this. So it's kind of introduction. But now, with the MDPs, you have a very good reference about it. The second interesting kind of bifurcation about this is belief space. Belief space planning is actually doing this. What happens if now what we consider is all these possible outcomes after executing a probabilistic transition, right? When you have a probabilistic transition, there's things that are going to happen, not always what you think. Maybe there's a distribution of them, a discrete set, whatever, right? So if you think about it, these information spaces could be equivalent to configuration spaces. Okay, what we are adding here, if for configuration spaces, what we were doing is augmenting the 2D space or 3D space to consider all dimensions on the mechanism or other things. With this, we are adding this new dimension of, okay, now you can have perturbations, and this is all possible outcomes, right? So think about it as a new dimension. In belief space, we could also include additional variables, right? It's basically, I don't know, maybe you want to include uncertainty. So this is your new variable. X, Y, orientation, and uncertainty. You need to think about it, how to represent this, right? Because it's not so straightforward. What is uncertainty? It's from a single variable. It's from each of the variables. What is this, right? So I'm not getting into details, but just think about it as new extra dimension that we are adding to the problem. How to propagate states. This is also a complicated problem, right? So now your state includes uncertainty, so how can you propagate this? Okay. If you want, if you're interested, there are some papers in Canvas about belief state planning. Some of them are using RRTs, others are using other variants. In general, what they include is this notion of uncertainty, like into planning techniques we have used before. Again, I didn't explain much about this, but if you're interested, take a look at the papers. I think they are very representative. Some examples of them. For instance, we have particle RRT. This is just an extension of the RRT, but it's considering uncertainty. So when you have a state, you will have this plus your uncertainty. It uses a particle filter to model this uncertainty. So that means that you do rollouts at each node, you calculate a little bit the outcome, you calculate uncertainty. It's a little more involved. At the end, you see that considering uncertainty takes more calculations, right? But it's kind of interesting because it's capturing this idea of, okay, if you don't know what's going to happen if you execute something, like for instance this robot moving here, then maybe you want to test out things more, right? So this is the idea behind. Okay, another is assuming maximum likelihood observations. So this is an example where light means that you have more certainty of what's going on. Dark means that you don't know anything about your state. So what we see here is that the shortest path in this example is going straight. But this might not be a good solution. Why? Because maybe first what you want to do is get certainty on your state. So that's why the algorithm, after assuming this uncertainty, is taking you to regions, clear regions. And once you get here, then you are ready to reach the goal. Okay, so it's a little bit the motivation. Again, here what you will need to do is how to propagate this uncertainty. So this is usually the main issue. Maybe this is a toy problem, but you will see the explanation in some of the papers that I put in Canvas, in particular this one, right, from Platt. And well, the topic goes very deep, right? So today I just explained like the basics with MDPs, a little bit of examples, but it's just highlights, not really like any serious explanation. And if you want to take a look at the papers, then I think, yes, you should be doing this. Also, soon we are going to ask groups to be formed. So if you haven't already submitted to us, our TAs, or me on Telegram, groups, I think it's time now. So maybe after class we discuss a little bit about projects. If you have a small team, you send this in Telegram, and we will start doing groups for class. Okay, so this is something that maybe you want to do just after we finish. You talk to each other, or maybe you send us now in Telegram this information. But we hope that by next week we start having, at least on Monday, we start doing final groups. All right, very good. Yes. We have 2 more lecture seminars. So it's going to be class next Monday. It's going to be class next Friday. And from there, we will spend time doing final projects. Thank you.